Any system will have a time response which consists of two parts. So, time response will have transient part of the response and steady state part of the response. The various parameters in the transient response are peak overshoot, rise time, peak time, settling time, and the steady state response you have steady state error. So, all these performance indicators will tell us how good the system is, how fast the system is responding to the inputs. So, to improve the performance, when I say the word improving the performance means you may have to see that the settling time required for the response to be reduced. Similarly, the peak overshoot has to be reduced, and how to minimize the steady state error. So, improvement of transient response means reducing the rise time, peak time, settling time, and peak overshoot also to be reduced within the limits. Similarly, improvement of steady state response is nothing but reduction in the steady state error. So, a controller, PID controller, is nothing but proportional, integral and derivative controllers are useful to improve the steady state and transient performance of the system. That is why it is represented in the form of block diagram in a closed loop control system. You have a controller whose transfer function is represented by GC of S, and the original system is represented like this, and then this is the output and this is the feedback you have. So this GC of S is a controller here. This GC of S is a controller. That controller is to improve the performance of the original system, which has got all these performance indicators. So, depending on the requirement, we need to minimize or improve the transient response as well as steady state response. So, GC of S is the controller. They are categorized here, the controllers, as P controller means proportional controller, then I controller, integral controller alone, then D controller is nothing but derivative controller, then combination of PI, combining P and I, then combining P and D, and finally combining P, I and D. So, all these are controllers and they are meant for improving the performance, either transient or steady state or both. Let us consider P controller alone. This is nothing but proportional controller. So, the output of this controller is proportional to the input signal and it is represented by Kp. So, let us consider the purpose. The purpose of this proportional controller is to change the transient response. Purpose of this controller, proportional controller, is to change the transient response, but it cannot eliminate the error completely. The transfer function of this controller is represented by Kp. So let us consider g of s of the system as 1 by s into s plus 10. This is without P control, without proportional controller. Now, the characteristic equation of this system, is s square plus 10s plus 1 equal to 0. And if you see the omega n, the undamped natural frequency of the system is 1 radians per second. And its zeta, the damping coefficient, can be determined from this 10, that is 2 zeta omega n equal to 10. Omega n is 1, so the zeta value is 5. Now, the damping coefficient and omega n you have determined for this system without P controller. Now add with controller, with Kp adding to the system, the function becomes Kp by s into s plus 10. So the closed loop transfer function now becomes Kp by s square plus 10s plus Kp. So the characteristic equation of the system with Kp, proportional control, is s square plus 10s plus Kp. Let us say Kp value, you want to have this controller to improve the performance or to change the performance. Kp say 100. When I put Kp as 100, the characteristic equation becomes s square plus 10s plus 100, and omega n is 10 radians per second, and 2 zeta omega n is 10 and omega n is 10 here, so the zeta value becomes 0.5. So the damping coefficient with controller having the value of 100 has become 0.5. You can see now zeta is 5 without controller, zeta is 0.5 with controller. So there is a reduction in the zeta. With Kp. So when zeta is reduced, the damping coefficient, the peak overshoot of the system, MP, it is given by e power minus zeta phi under root of 1 minus zeta square. So as zeta decreases, the peak overshoot increases. So similarly, the settling time Ts is equal to 4 by zeta omega n. So as zeta reduced, the settling time is also increased. Means the transient performance is not improved, but it is becoming worst when you have Kp of 100. So the values of Tp and Ts and peak overshoot you need to choose such that the value of Kp will help us that the performance should not be too much worst in this case. So the peak time is also given by pi by omega n under root of 1 minus zeta square. So even the peak time also is increased because of the Kp inclusion alone. I controller, this is nothing but integral controller. So the purpose of this integral controller is to reduce the steady state error, and the transfer function of this integral controller is Ki by S. That means this controller adds one pole at origin. This controller adds one pole at origin. So addition of pole at origin means the type number of the system is increased by 1. So as the type number is increased, the steady state error will be decreased. So that is the advantage of integral controller, that steady state error is reduced. But the stability got affected by adding one pole to the system, and that too at the origin. For example, let us consider the system transfer function as 1 by s into s plus 10 without controller. Now, as it is, when you look at the function without controller, the type number of the system is 1. The type of the system is 1, and the characteristic equation is s square plus 10s plus 1. This is the characteristic equation of the given system, and by looking at the characteristic equation, you can say that whether the system is stable or not. You can see that all the terms starting from 2, s power 2, s power 1, s power 0. So it has got all the terms, and by looking at this roots of the characteristic equation, even if you find, you can say that system is stable. Now let us add a controller. So a controller is added to the system. With controller, the function becomes Ki, and S is already there here, and another pole is added at origin because of the integral control action. So it becomes s square into s plus 10. So the closed loop transfer function for this becomes Ki by s cube plus 10s square plus Ki. That means the type number is increased. Earlier it was type 1, but now the type of the system is increased to 2. No doubt, because of the type increased, the steady state error will be reduced. But when you look at the characteristic equation, the characteristic equation of the system is s cube plus 10s square plus Ki. So all the terms are not available in the characteristic equation. One term is missing here. You can see s power 3, s power 2, then s power 1 is missing here. Directly you have got Ki, s power 0. So the s coefficient or s term is missing. So we can say that system is unstable. System is unstable because there is one term missing in the characteristic equation. That means we can say that the stable system without controller, the stable system, it has become unstable because of the integral control action. When you use alone Ki by S, that means integral controller, no doubt the steady state error is minimized, but the stability got affected because of the integral control action. That is the limitation of integral controller. The next controller is D. D controller is nothing but derivative controller. Derivative controller. So the purpose of this derivative controller is to improve the stability. To improve the stability, and the transfer function of this derivative controller is derivative constant multiplied by S. So this derivative controller adds 1 0 at origin. It adds 0 at origin. So when the 0 is added, what happens to the type number of the system? Type number is decreased because it is in the numerator. So the type number is decreased because of the derivative controller. With this, the steady state error may shoot up. The steady state error may shoot up, but the stability aspect is improved. So let us consider the example that g of s of the system is given by 1 by s square into s plus 10. This is without controller. I am trying to explain that addition of this controller will affect stability and steady state error. How? So without controller, the function is this, and the type number of this system is 2, and the characteristic equation of the system is s cube plus 10s square plus 1. So as it is, you look at the equation, there is one term missing again here. So s term is missing. The necessary condition is not satisfied. So the system is unstable, we can say. Now with controller, you add a controller that kd times s to this original system. So with controller, the function becomes kd into s by s square into s plus 10. So this s and s gets cancelled. So this function becomes kd by s into s plus 10. So the characteristic equation, now the characteristic equation of the system is s square plus 10s plus kd. You can say now the type number has been decreased because of the addition of the derivative controller. So when the type number is decreased, the steady state error will shoot up, and the characteristic equation, when you look at, all the terms are existing. The no term is missing, like s square, s and s power 0. We can say that it is a stable system. So compared to the system without controller is already unstable, and that has become stable here because of the addition of derivative controller, but steady state error is increased because of the derivative controller. That is the limitation of derivative controller. So PI controller, we need to combine proportional has got Kp plus integral, this is Ki by S. So to get the advantage of both proportional and integral controllers, we need to combine them. So the function of this controller, the transfer function of this controller becomes Kp plus Ki by S. So we can say this as Kp into S plus Ki by S. So integral controller alone is adding a pole at origin, but because of combining proportional and integral, now you can look at the transfer function of the PI controller, that it adds one pole at origin. It adds one pole at origin. So certainly the steady state error is decreased. Now in the numerator you can see that there is an S term, that means there is a 0 also. It adds finite 0. It adds finite 0 to the system. So this will improve the stability of the system. So that is the advantage of combining proportional and integral controller. The stability also is not affected much, but steady state error is reduced. Integral controller alone decreasing the steady state error, but stability has got affected with integral controller alone. So combining these two, having an advantage of stability aspect as well as steady state error. So let us consider the example again to explain the advantage of PI controller. Consider the function as 1 by S into S plus 10. So as it is, the type of the system is 1 because there is one pole at origin, and the characteristic equation is S square plus 10S plus 1. So by looking at the characteristic equation, you can say that system is stable. System is stable. Now with controller, when controller is added to the original system, the function becomes skp plus ki in the numerator, and in the denominator there is a term now s square into s plus 10. So type of the system is increased to 2. Type 1 system has become type 2. So steady state error is directly proportional to the type number. So when type increases, the steady state error is improved, means steady state error is decreased. Now looking at the characteristic equation of the system with controller, it becomes s cube plus 10s square plus skp plus ki. So the characteristic equation also has got all the terms, means no term is missing in the characteristic equation because of combining kp and ki. So still the system is stable. So stability is not affected. Without controller, system was stable, but even now system is stable. So steady state error is improved and stability remains. So PI controller has got that advantage. Eliminating the disadvantage of integral control alone, PI controller is preferred. The next one is PD controller. This is proportional, has got Kp plus derivative, that is Kd into S. So the transfer function of this controller is Kp plus Kd into S. So it adds 1 0, that is finite 0. Earlier derivative controller alone, it has got 0 at origin. but now because of the addition of proportional to the derivative, the 0 is there in the system but not at origin, but it is a finite 0. So this will be towards left. The 0 is shifted from the origin towards left, which will improve stability, improve the stability without affecting steady state error, without affecting the steady state error. For example, consider function without a controller 1 by s square into s plus 10. As it is, the type of the system is 2 here, because number of poles at origin is equal to 2, and the characteristic equation is s square s cube plus 10s square plus 1. So originally the term s is missing here. We say it is an unstable system, necessary condition is not satisfied. Now with controller, this kp plus kds, the function becomes kp plus kd into s finite 0 added to the system by s square into s plus 10. So the type number has got no effect. That means steady state error is not affected. Earlier also it was type 2 system, now also it is a type 2 system. But stability, to see that, we need to write the characteristic equation. Using that we can say whether the system is stable or not. So this becomes s cube plus 10s square plus kd into s plus kp equal to 0. So kd and kp, we need to choose the values according to the requirement, but when you look at the characteristic equation, you have all the terms existing starting from s power 3 to s power 0. So we say that it is a stable system. So an unstable system has become a stable system with the PD controller. That means stability is improved. The stability is improved with the PD, but steady state error remains unchanged. So now, to have the advantage of proportional, integral and derivative controller, all three are combined. PID controller with proportional gain Kp plus integral Ki by S plus derivative Kd into S. So all the three are combined, that becomes PID controller. So the transfer function of the PID controller is Kp plus Ki by S plus Kd into S. So this can be written as Kd into S square plus Kp into S plus Ki by S, the transfer function of PID controller. So the effect of this controller, it adds one pole at origin, So as it is, the steady state error is decreased. Now there are two finite zeros. PID controller adds two finite zeros to the system. So that improves the stability aspect. This improves the stability. So to explain that, consider a system without controller, 1 by s square into s plus 10, without any controller, So the type of the system is 2, and the characteristic equation s cube plus 10s square plus 1 equal to 0. So unstable system. Now you add a controller with controller, the function becomes kds square plus kps plus ki in the numerator, and s cube, s power 2 becomes s power 3 now into s plus 10. So you can see that the type is now 3. So the steady state error is improved because type number is increased. And if you write the characteristic equation of this system, s power 4 plus 10s cube plus kds square plus kps plus ki equal to 0. So all the terms exist in the characteristic equation starting from s power 4 to s power 0. So we say that the system is stable. So an unstable system without controller, the stability is improved because of the addition of 2 finite zeros, and also the steady state error is improved. So to improve the overall time response, which includes transient as well as steady state response, the PID controller is preferred.